Geometry 2-5 Postulates and Paragraph Proofs. Another time when Mr. V is not writing anything. Yes, that's the way it is because there's a lot to write here, and I'd rather not spend an hour on a video writing, but instead let you pause as you need to catch up. So we're going to learn a new word here, and that is postulate or axiom. We pretty much never use the word axiom in this class, but we do use the word postulate. Postulate is a statement that is accepted as true without proof. So you could just say without proof, something that you just know. And that's what a postulate is. It's something that's true and you don't need to prove it that it's true. So I'll try to think of like some common everyday examples, but I don't have any for you right now. So what we're going to do here is we are going to write out this whole graph here, or this chart. So you're going to start the chart with postulates that have to do with points, lines, and planes. And you need 1, 2, 3, 4, 5, 6, 7 columns, or 7 rows and 2 columns. And I'm going to talk you through this whole thing. And so just pause as you need to try to catch up. Now, here's something that I want you to really pay attention to. And all of these postulates in the book, they have numbers associated with them. I don't want you to really concern yourself with these numbers. I just want you to understand the concept. So in a proof later on, when you have to prove something, I don't want to see postulate 2.1. I want to see through any 2 points, there is exactly one line. So you can pretty much ignore these. These are just here kind of to help keep everything organized. I don't want to see this on a test or on your homework. I don't want to see the number. All right. Okay. So this first postulate here is through any 2 points, there is exactly one line. And so anytime you have 2 points, so for instance, I have a point P and a point R, you can draw a line right through them. Doesn't matter what the points are, where they are, you can draw a line through them, and there's a line PR. And so we can call this line M or line PR, whatever. The second one, through any 3 points, any 3 non-collinear points, there is exactly one plane. So here I have 3 non-collinear points. So remember, collinear means they are in one straight line. These 3 points are obviously not in one straight line. And so you can draw a plane through them. So this is plane K here. So these are postulates. These are things that we just accept as true without having to have extra proof. This next postulate, a line contains at least 2 points. So any line you create or any line you see has to have at least 2 points. It actually will have many more than that, an infinite number of points, because it's a line, but it has to have at least 2 points. And here we have line N. This fourth one here, a plane contains at least 3 non-collinear points. So these are just kind of the reverse, just saying it in a different way for these, the first 2 that we did. The fifth postulate is if 2 points lie in a plane, then the entire line containing those points lies in that plane. So if I have a piece of paper, if I have a piece of paper that is my plane, if I have a line if I have these 2 points that are on this piece of paper that is a plane, then the line that I would draw on that piece of paper is contained on that plane. So all it's saying is, if your 2 points are in a plane, the line that I draw between them or through them will also be on that plane. That's all that this is saying. The sixth one, if 2 lines intersect, then their intersection is exactly 1 point. If 2 lines intersect, they intersect at 1 point. If 2 planes intersect, their intersection is a line. So I've got 2 planes drawn here, and where they intersect is a line. So those are the postulates that we're going to look at today. And then here are some examples, the kinds of things you might see on the homework. So we're going to have some statements, and we have to decide, is this always, sometimes, or never true? And then we've got to explain. All right. So number 1. Two coplanar lines intersect. The point of intersection lies in the same plane as the lines. So if I have two lines that intersect, and the point of intersection, so the two lines that are coplanar, meaning they're on the same plane, if they intersect, then that point in which they intersect lies on the same plane as the lines. So if I have a line here and a line here, and they intersect, that point, will that always be on the same plane that the lines are also contained in? And I would say that is always true. There's no way I can draw the lines in such a way that their point of intersection is not on the plane. The lines are both contained on the plane, so they must also, their intersection point must also be on the plane. All right, 4 points are 4 points are non-collinear. Is this sometimes, always, or never true? 4 points are non-collinear. So we maybe for this one need to draw some points. So I could draw 4 points. Notice how these 4, they are not collinear. But look, last time I drew 4 points right in a row, and they are collinear. So this is a sometimes true statement. Sometimes it's true that they're non-collinear. Sometimes it's not true and they are collinear. All right, let's do some more sometimes, always, or never true. Number 3, two intersecting lines determine a plane. Two intersecting lines determine a plane. That's an interesting one. So if I have two lines that intersect, does that determine a plane? I would say so. Because if I have two lines, just like I drew last time, if I have two lines, then I also have 2 points on each line, and I can include the intersecting point. So that means this point and the intersection point, those are 3 points, and 3 points, any 3 points that there are, that will define a plane. So I've got 3 points and a plane. I would say that's always true. Now let's look at this one. 3 lines intersect in 2 points. Okay, let's draw 3 lines. I've got 1, 2, 3 lines. 3 lines, look, they intersect in 2 points. Now I have to decide, is there another way I could draw 3 lines where they don't intersect in 2 points? What if I were to draw 3 lines like this? Boom, they're only intersecting in 1 point. What about 3 lines like this? 1, 2, 3, and these are all parallel to one another. They never intersect. So, yes, we can draw 3 lines and they intersect in 2 points. We can draw 3 lines and they intersect in 1. We can draw 3 lines that don't intersect at all. So this is a sometimes true. Oh, look, and last time I even drew one where they intersected in 3 points. Look at that, smarty pants. Past Mr. V, he's smarter than present Mr. V. All right, the proof process. Now, The proof process, in the book, they're going to talk to you about a paragraph proof. I don't want you to do a paragraph proof. Whenever it says do a paragraph proof, don't. Do a 2-column proof. That's all I really care about. That's how I want you to look at this and think about this. So you're going to do a 2-column proof, whether it tells you to do a paragraph proof or a flowchart proof or any of those other things. Just do a 2-column proof. That's what I want from you. Okay, so the proof process. So first step 1 is to list the given information. We're going to do one together here, so just write this down and then we'll do it together. List the given information and draw a diagram. Always draw. In geometry, you do so much better if you draw your diagrams. Step 2, state the conjecture to be proven. So anytime you're given a proof, you're going to be given information, and then you're going to be told, what do you want, what are you supposed to prove given this information? All right, so you'll see that in a minute. Step 3, make a plan. So start thinking about, okay, deductive argument, outline your statements, logical order. Think about how are you going to prove this statement that they're asking you to prove given this information and given all of the stuff that you know. And then step 4, you need to reason for each of these things in your plan. You need a postulate or a theorem that's going to help you with that. And then step 5, state what it is that you have proven. You got to rewrite your conjecture. Okay, so make sure you pause and you write everything down, and then we're going to do this one. Okay. Here is the example that we're going to do together. Okay, here's the given. Here's in step 1, this is the given information. M is the midpoint of xy. So we just write down M is the midpoint of xy, segment xy. Notice how there aren't arrows on the side of this? This means segment xy. And so I write down, I write this down, and then I write down I draw the diagram. Here's segment xy, here's M in the middle. Conjecture, here's what they're telling you to prove. That xm is congruent to my. So we need to prove that xm is congruent to xy. All right, so here is our this is one of the shortest and easiest proofs you'll ever see. So here's the 2 columns. On one side you write statements, on the other side you write reasons. So you just do like a big T-table, statements on one side, reasons on the other. And then the first thing you write in the statements is the given. M is the midpoint of segment XY. And your reason is the given. And now we know that if M is the midpoint, then XM equals XY. And that is the definition of midpoint of a segment. So conjecture, this is a one-step proof here. We didn't need to make a plan. We just know that XM is congruent to MY because of this definition of the midpoint of a segment. All right, so this is a kind of a super basic proof, and we will, going forth, be doing much more involved proofs. But here's your idea of how to get started. And that is the 2-5? So get to work on your homework, and let's keep plugging away.